You ever write some code, hit run, and just take a second to wonder what's really going on under the hood? Like, how does that text you wrote become a program that actually works? Well, today, we're going to demystify the very first steps a compiler takes to figure out what you're telling it to do. I mean, it's a huge question, right? We spend all this time making our logic just right, but when it comes down to it, to the computer, it all just starts as a bunch of characters in a file. So how does it bridge that gap? How does it go from what's on your disk to something it can actually run? Let's dive in. Okay, so the first thing you really got to wrap your head around is this. When the compiler first opens your file, whether it's a .go file or anything else, it doesn't see code. Not yet. It just sees plain old text. No, seriously. At this point, your masterpiece is no different than a simple .txt file. The compiler has zero concept of what a function is, or a variable, or a loop. Its very first job is just to read this long string of characters and start looking for patterns. All right, let's get into the nitty-gritty. The first official step the compiler takes is a process called Lexing, and its entire job is to turn that raw, meaningless blob of text into small, meaningful chunks. So check this out, a super simple line of Go code. To you and me, that's obviously a variable assignment, but the compiler sees it one character at a time. X, then a space, then colon, then equals, then 1, 0. It needs to group these things together into something useful. And this is where the magic starts to happen. This is that grouping process in action. The compiler scans the text and spits out what we call tokens. So the single character X becomes a token called an identifier. The two characters /equals get bundled together to become a single assignment operator token. And 10 becomes a number literal. You see, these tokens are the absolute smallest, meaningful building blocks of the language. Think of this stage as like a big cleanup crew. It's not just grouping characters, it's also throwing out all the junk it doesn't need. All those extra spaces and tabs you use for formatting, gone. The comments you wrote for yourself, stripped out. What's left is a nice, clean stream of tokens. And here's a fun fact. This is your first chance to break everything. If you write something weird like 1x, the Lexer has no idea what token that's supposed to be, and boom, the whole process just stops right there. So if we're going to put a nice, neat definition on it, that's what Lexing is. It's the process that takes that raw stream of characters from your file and turns it into a structured sequence of tokens. We've officially gone from meaningless text to a list of symbols the compiler can actually work with. Okay, so now we've got this list of tokens, an identifier, an assignment operator, a number. That's great, but what do they actually mean when you put them in that order? That's where the next step, parsing, comes into play. Right, so if Lexing was about identifying the words, parsing is all about understanding the grammar of the sentence. It looks at the order of the tokens to figure out the actual structure of what you're trying to say. The parser has the rulebook for the language, and it's checking if your sequence of tokens follows those rules. And to get technical for a second, that's the formal definition. Parsing is all about analyzing that stream of tokens to make sure it follows the language's grammar. It's not about individual symbols anymore, it's about how they fit together to make valid statements, expressions, and the whole shebang. Here's the thing though, when parsing works, it doesn't just give a thumbs up and say, yep, this is valid code. No, it does something way cooler. It builds a completely new and much more powerful representation of your program. And this is the grand prize. It's called an abstract syntax tree, or AST for short. It's incredible. As you can see, that flat line of text, our if statement, gets transformed into this hierarchical tree structure. The parser sees the if and makes it a main node. Then it figures out the condition, x greater than 5, and attaches it as one branch. And it sees the code inside the curly braces and attaches that as the other branch. This tree is the true, logical structure of your program. And this is the key takeaway here. We are so past just looking at text now. The compiler doesn't care anymore if you use tabs or spaces or how you formatted things. All that matters is this logical tree, which it can now navigate and actually start to reason about. Okay, I know what you might be thinking. This feels a little complicated, right? Lexing, then parsing, building a tree. Why go through all this trouble? Why are these steps so critical? Well, it's because without that AST, the compiler is basically powerless. It can't do any of the smart stuff we rely on it for. It wouldn't be able to check your types to see if you're trying to add a number to a word. It would have no way to optimize your code to make it run faster.
And it definitely couldn't generate the final machine code that your computer actually executes. Lexing and parsing, they're the foundation for everything else that follows.
So if you need a super simple way to keep all this straight in your head, here it is. Just think of Lexing as asking, what are the ingredients you gave me? It's just identifying the symbols. Parsing, on the other hand, is like looking at the recipe. It asks, how are those ingredients arranged? Does this arrangement actually make a valid dish? Okay, so let's say you're in a job interview and you want to sound really sharp. You need that one perfect, concise sentence to explain this whole process. We've got you covered. Boom. There you have it. That one sentence perfectly nails the entire process we've just talked about. And the best part is, now when you say it, you actually get what every single part of that sentence really means. You understand that journey from a text file all the way to a structured tree. So, we've done it. The compiler has built the tree. It knows the structure of your program is valid. The grammar checks out. But that brings up a whole new problem, doesn't it? Just because the grammar is right, does the program actually make sense? I mean, is it okay to add the number 5 to the word hello? The structure is clear, but is it correct? Well, finding that out is the job for the next stage, type checking. And we'll dig into that in a future explainer. Thanks for joining me.